Hey, everybody. Thank you for joining us for the next session of our JavaScript Buildathon. My name is Anna. I'll be your producer for this session. I'm an event planner for Reactor, joining you from Redmond, Washington. Before we start, I do have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenters to answer. Our session is being recorded. It will be available to view on demand right here on the Reactor channel. With that, I'd love to turn it over to our host for today, Carlota. Thank you so much for joining.
Hi everyone. Welcome everyone, and thank you, Anna, for the introduction. So welcome to the last live streaming of the JavaScript AI Buildathon. I'm Carlotta Castelluccio, AI advocate at Microsoft in the DevRel team, and I'll be your host for today. But first of all, what is the JavaScript AI Buildathon? So it's a virtual skilling series that highlights modern AI patterns using JavaScript. I'm mostly a Python developer, and as a Python developer, sometimes I feel kind of privileged for the amount of resources that are available for Python devs when it comes to AI. But we know there's lots of communities with JavaScript developers, and please let us know if you are a JavaScript developer or what's your programming, what's your main programming language. We know there's lots of JavaScript developers who are eager to explore and experiment what's possible with AI, or maybe they are already building AI solutions. So this program is exactly designed to kind of bridge this gap. So let's look at the roadmap. As I say, this is the last live stream of the program, but it's not the end, absolutely. So we have today's live stream and then the follow-up AMA on Discord, and I will give you all the details after the session. We closed the first phase of the program where we hosted several sessions about local AI, RAG, multi-agency. And all these sessions have been recorded and are available on demand. And Anna will post a link in the chat so you can catch them up if you miss them. And starting from Friday, we launch the next phase, which is the hack. So it's your turn. It will be your turn to apply what you learned and build your agentic solution. And the good news is you are not alone in this. You don't need to hack alone. There's a huge community on Discord of like-minded peers where you can find collaborators, you can share ideas and ask questions. And once you join the Microsoft Foundry Discord server, you'll find a dedicated channel with the name of this initiative. Again, all the links, you can see the link on the screen, but the link will be shared in the chat as well. Okay, so now it's time to bring on stage our speaker for today, my great colleague, Wasim. Wasim, hi, hello, and
hello.
Take it from here.
Yeah, thanks. Thanks for having me. Thanks, Carlota. Yeah. So hi, everyone. Thanks for joining us today. So yeah, during this session, I'd like to show you how to design and build multi-step AI agents that can actually survive production, because that's hard. So the core idea I want you to remember is simple. A good agent is a system. It's not just a prompt, a huge prompt. So for this, we'll combine three things. We'll combine Agentic RAG, we'll combine MCP for tool integration, and we'll combine a set of reusable design patterns. And one mental model to keep in mind the whole time is that tool calls are just distributed system calls. They fail, they time out, and they may return partial results, just like any other backend system. So here's the roadmap. First, we'll look at why agents fail in production. Then we'll cover Agentic RAG with a concrete example. After that, we'll introduce MCP and why treating tools as contracts changes everything. And then I'll show you 4 design patterns you can reuse across projects. And finally, we'll walk through architecture and a production checklist. But before we dive into the technical details, let's set the stage for what this session is and isn't about. So this session introduces how to create scalable and reliable multi-step AI agents that can act by using tools and external processes as part of their reasoning. We are going to focus on real-world engineering challenges, such as reliability, which is how to make sure our agent doesn't break down when it handles complex tasks. We will also focus on scale, and that's how agents can handle lots of requests or large tasks. And also we'll focus on maintainability and also dealing with dynamic external signals like changes in data sources or environments. So these are the key technical challenges we face when moving from a cool demo to a robust application. So the core concepts we'll cover, as I mentioned, include Agentic RAG, which is a smarter way of a retrieval augmented generation process. We'll also cover MCP, which is Model Context Protocol, for connecting to tools with a clear contracts, and some structured multi-agent design patterns that bring order to the chaos of multiple steps and decisions. So all of this is underpinned by adopting an engineering mindset. We need to treat our AI agent workflows like we treat distributed systems. That means establishing clear flows of state, defining contracts for each component, handling errors and timeout gracefully, and building in observability to monitor and debug what's happening inside the agent. So to set expectations, this session is not about clever prompt tricks or prompt engineering. It's about good software engineering discipline applied to AI agents. So hopefully by the end of this talk, I want you to be able to break an agent into well-defined components, coordinate work across multiple steps in a controlled way, integrate external systems like APIs or databases safely via proper interfaces, and debug the agent's behavior without resorting to guesswork. So to keep things concrete and relatable, I'll use a single running example throughout this talk. Imagine we are building an AI agent to help plan a travel itinerary with specific conditions. So in our scenario, the user wants to plan a 4-day trip. They're interested in doing some hiking during the trip. They have a certain budget in mind, and they also want to include one fancy dinner as a special treat. So this scenario will serve as our example as we discuss concepts. It's a great case because it's inherently a multi-step task with constraints. There are a bunch of subtasks like choosing a destination, planning daily activities, making bookings, and constraints that the agent has to consider, like budget, the number of days, and that special dinner. So it will likely need to use multiple tools or data sources for things like flight info, hotel information, hiking trails, restaurant recommendations, etc., etc. And it will have to decide what actions to take and in what order. But if travel isn't your domain, so mentally swap this for logs, tickets, approvals, or deployment. What matters is that this is a multi-step task with constraints, tools, and decision. So here's how our story unfolds. We will start with failure modes, then building blocks, then patterns, then introduce a reference architecture, and finally, operations. So why are multi-step agents so hard to get right? Let's talk about the common failure modes that can happen to our travel planning agent or any complex AI agent when it's out in the real world. So as our agent tries to plan the trip, the following failure can happen, and they will happen actually. So first one is that sometimes the agent might pick the wrong tool for a task. For example, it might try to use a hotel booking tool to look at hiking trails. Clearly not the right choice. With many tools available, choosing incorrectly is a real risk. Also, our agent might call an external API, say for a flight search service, and that call could hang or take too long and timeout. Also, even if the agent picks the right tool, that tool could respond slowly or return only partial data due to an error. These kind of partial failures can confuse the agent, actually. And as the agent moves through multiple steps, it might lose track of earlier details or even sometimes overwrite them incorrectly. For instance, perhaps the agent initially picked Paris as a destination, but later in the conversation, it forgets that it was Paris, and then it's just a restaurant in, say, London. So this drift in the agent's state or memory can happen in longer sessions if we are not careful. And finally, these errors can start to compound. So a small mistake in step 2 can lead to bigger mistakes in step 6 or 7, and so on. The agent might even get stuck in a loop of trying the same failing tool over and over, and each time amplifying the failure. So let's take some time actually to dig deeper into this compounding error problem, or what I call the reliability task we pay as we add more steps to an agent's process. So imagine we are watching a really cool demo of an AI agent, and the presenter types a request, hits enter, and the agent miraculously performs a complex task flawlessly. Now, you are inspired, you take that same AI agent and deploy it into your own project, and suddenly it's making all sorts of mistakes. It's hallucinating answers, getting stuck in loops, or running into error from the tools it calls. So the instinct might be to blame the AI model. Maybe we need a more powerful model or a cleverly engineered prompt. But in reality, what's happening is more fundamental. It's mathematics and system complexity at work. So the compounding error problem means that even if each step of your agent is pretty accurate, the chance of all steps succeeding together drops dramatically as you add more steps. So I call this the reliability task because each additional action or tool call basically taxes your overall success rate. So consider our travel agent example. To plan that trip, the agent might have to do as many as 10 different things. For instance, it parses the user's request, checks flight options, find hotels, look up hiking trails, and verify the company's travel policy, compare the price on different sites, confirm dates against the user calendar, handle payments, and maybe a couple of more steps. So that's a lot of moving parts. If our agent has a 95% chance of getting each step right, which is extremely high for an AI, the probability it gets all 10 steps correct is in one go is only about 60%. So that's like flipping a coin and hoping everything works out. Now, if we had 20 steps. So even at 95% accuracy each, the success rate falls to roughly 36%, meaning it fails almost 2/3 of the time. So in practice, almost perfect at the step level turns into mostly broken at the system level. So it's a harsh reality when the reliability task. We need to start treating our AI agent not as a mystical black box, but as non-deterministic software components that require good software practices. So we need two big changes in mindset and design. The first one is selective autonomy. We should not let the agent do everything autonomously for high-stakes decisions. It's like flying the plane. So even if the autopilot is great, you still want a human co-pilot for critical moments. In our context, use the AI for the heavy lifting in generating options or processing data, but insert a human approval step for the really important decisions. For example, our agent could draft a travel plan, but a human might errors we talked about. And each time a human checks in, you reset the error probability back to 100% success for that step. Second, that's trace level observability. We need better insight into what our agent is thinking and doing at each step. Traditional logging might tell us that something bad happened, but we need to know why it happened. Like, was it a bad piece of retrieval data? Did the agent misunderstand the user's request? Did the tool call fail? So by building trace level observability into our agent, we can actually watch the agent's internal decision-making process or its chain of thought. So at the chain of thought, like for each tool call it makes. We can actually watch the agent internal decision-making process. This way, when the agent fails at, say, step 7, we can dive into the trace and figure out exactly where things went wrong and why. So remember that the gap between a cool demo and a reliable product isn't about adding more features or just using a bigger model. It's about adding more discipline and structure. If we want to move from, hey, that demo was cool, to this is driving real business value, we have to solve the compound error problem with strategies like human in the loop, rigorous error handling, and transparency. Now, with these challenges in mind, let's start looking at solutions, beginning with classic RAG and Agentic RAG. So classic RAG, which you might already know, retrieval augmented generations, says that we always retrieve context. And that's exactly where the problems start. In our travel example, we end up cramming everything, weather data, hotel options, flight details, restaurant suggestions into a single prompt, all of it all at once. And that kind of prompt is fragile. It's harder for, it's harder for the model then to reason clearly, easier to miss constraint, and more likely to break at the task as the task grows in complexity. So this is the baseline we're trying to improve with Agentic RAG. So agentic systems use conditional retrieval instead of always-on retrieval. This means an agent fetches information only when it's needed. Conditional retrieval plus validation loops dramatically reduce failures. So the agent pauses, checks for checks constraints, and only then proceeds. So if you want to go deeper on advanced agentic RAG patterns, my colleague Pamela Fox has an excellent session linked here. But for our session for today, the key takeaway is, well, sorry, my slides are moving alone. The key takeaway is that retrieval should only be intentional. The next core concept is MCP, which stands for Model Context Protocol. It's essentially a protocol layer that enables safe and consistent interactions between our AI agents and external system or tools. You can think of MCP as a sort of a middleman or a translator that sits between the AI and the actual tools or services that the agent might use. One of the key principles here is separation of concerns. With MCP, the actual tool implementations, like the code that actually calls the API or perform a database query, run on a separate MCP server. Meanwhile, the agent reasoning, the large language model doing the thinking, runs on a client side. So the agent communicates with the tool by sending a request to the MCP server, which then executes the tool and returns the result. This means the agent itself doesn't need to know the nitty-gritty of how the tool works. It just needs to know the interface or contract. So this leads to modularity and scalability because tools are decoupled from the agent's core logic. Each tool can be developed and maintained independently. You could have different teams or services owning different tools. One team manages the flight booking tool, another manages the weather lookup function. And as long as they all adhere to the MCP interface or the predefined input-output schemas and behavior, you can plug them into your agent without changing your agent's code. You can also scale these tool services separately. So if one particular tool is getting hammered with requests, you can scale up just that part of the system. And yeah, essentially MCP allows for multiple teams development and independent scaling without changing the overall orchestration. Also, MCP brings in an important enterprise governance features out of the box. So because all tools interactions go through it, you have like a single choke point to enforce things like security and policy. For example, you can manage identity and permissions using a service like Azure AI Gateway, making sure the agent only calls services it's allowed to. You can implement throttling to prevent any tool from being overwhelmed. And you can even enforce organizational policies like data privacy rules or just or users limit in like one single place. So these governance controls are crucial when you're deploying agents in a company or production environment. So as a side note, for those of you who are interested in deploying MCP servers on Azure, there is a link on this slide to a blog post by my colleague Paul Yu, where he walks you through how you can deploy an MCP server on Azure Kubernetes Service, AKS, using something called workload identity. So now when agents leave demos and touch real system, security stops being optional, clearly. So the moment our travel agent can call APIs, access data, trigger side effects, it becomes part of our attack surface. So the rule is simple: never trust the agent. Trust the boundaries. With MCP, security lives outside the model. Tools run on servers. The access is gated by identity, and permissions are enforced before the agent ever acts with something like AI Gateway. In our trip scenario, the agent can suggest a booking, but only a tool with the right identity can execute it. No tool access through prompts, no hidden credentials, no the model decided to try something. We apply the same principles we use everywhere else: least privilege, explicit contrast, and audited execution. Now let's talk about costs, because agents are very, very, very good at spending money. Tokens, tool calls or tries, search, embeddings, reasoning loops, it all adds up super fast. So we design for cost upfront, not after we receive the invoice. So first, budgets are part of this state. We track token usage, tool calls, retries, and total execution time. Second, Agentic RAG helps control spend. We only retrieve when we must, no default search, no blind context stuffing. Third, Supervisor loops enforce limits. If agents hit a budget, it stops, summarizes, or asks for confirmation. So in our trip example, that means we don't keep searching hotels forever just to find a $2 cheaper option. So cost discipline turns agent from experiments into predictable systems. Another core concept that is so underrated is observability. And as I've said, multi-step agents are essentially doing a lot under the hood. They generate many internal actions. This is why we use traces. So a trace basically records a path. Records the path of a request through the system. That's why logs alone aren't enough. So traces tell the story end to end, what happened, where time went, and why we failed. So so far, we've focused on making agents smarter about when they retrieve information and safer in how they interact with tools. The next problem to solve is structure. How do we organize all of this logic to so it holds up the workflow as the workflow grows? This is where design comes in. So I want to walk you through 4 design patterns. Sorry about that. That bring order to multiple step agent system. Basically patterns that make agents predictable, reliable, and scalable instead of fragile and ad hoc. So the first one is the router or triage. Now imagine this as the front door or the air traffic controller for your agent system. The idea here is that when a user request comes in, the router agent job is to figure out what kind of request it is, and route it to the appropriate place. So the router essentially classifies the initial user query. It might determine, is this a travel recommendation request? Or is it a request to build a detailed itinerary? Or maybe it's something that needs a web search. So based on that classification, the router passes the query to a specialist agent that is best suited for that category of task. This helps keep the system predictable and efficient instead of like one agent attempting to use every tool under the sun, which can lead to confusion or the agent picking the wrong tool, as we saw. The router narrows down the problem space right at the start. So what does the router pattern help us prevent? A few things. It avoids wrong tool selection. Again, the agent won't try using, say, a restaurant booking tool to fetch a weather report, because the router sends the request to the right subset of tools. It also prevents off-topic tool calls and tool overload, where the agent might otherwise try a bunch of irrelevant tools and waste time. Essentially, it brings predictable routing in systems where multiple intents or many tools, so you know that a certain type of query will always go down a particular path. In our trip planning scenario, a router would examine the user's request, like plan a 4-day trip with hiking on a budget. Then the router might classify this request and decide to pass it to a destination recommendation agent if the user hasn't picked a destination yet, or if the user had said, for instance, I want a day-by-day itinerary for Paris, then the router could send that to an itinerary planning agent. And if the request was something else, like what's the weather in the mountains in October, maybe it would route to a web search function or a weather agent. So by triaging the query, we ensure the correct part of our system handles it, setting up for an accurate and reliable response from the beginning. Our second pattern is specialist agents with tool scoping. This goes hand in hand with the router pattern. Once the router directs a query to the right place, you want that place to be a specialized agent that's really good at its specific job. Instead of, again, one giant agent that tries to do everything, we have multiple smaller agents, each focused on a particular subtask. And importantly, each one only has access to the tools it truly needs. So what does this pattern prevent? It prevents a monolith agent that is hard to test. So a single agent that's so large and entangled that you can't easily understand it or debug it. It also reduces the risk of tool misuse because an agent won't try to use a tool it doesn't have, and avoids overwhelming the agent with irrelevant information or capabilities. Each agent stays focused on its job. So you would use specialist agents when your overall task is naturally decomposable into parts, or when different tasks require different skill sets or external tools. It's also useful when you have different teams responsible for different functionalities. Each team can own an agent and its tools without stepping on each other's toes. So in our trip planning scenario, this pattern is very applicable. We could design, for example, a destination agent that only has the tools and data needed to recommend travel destinations. It might use a tool for retrieving popular travel spots or checking weather or events in various locations. Separately, an itinerary agent could handle building the day-by-day schedule and making bookings with access only to booking and scheduling tools. And because the destination agent isn't concerned with how to book a flight, and the itinerary agent isn't concerned neither with picking the perfect city, it assumes the destination is already chosen. So each one can do its job more reliably. And if one of them has a problem, which could happen, it's isolated to that part of the system, which makes debugging and maintenance easier. All right, our third pattern, which is plan, execute, summarize, or PS. This pattern introduces a more structured approach to an agent's workflow by explicitly breaking the process into three phases: planning, execution, and summarization. Here's how it works. At the start, the agent creates a plan for how it will tackle the user's query. This is like the agent thinking out to itself. Okay, first I'll do A, then B, then C. After planning, the agent moves into the execute phase. In this phase, it will carry out each step of the plan, calling tools and performing subtasks as needed. And finally, once those steps are done, the agent enters a summarize phase, where it compiles the results of all the steps into a final answer or solution for the user. So this pattern prevents the agent's reasoning from being a black box. You no longer have to wonder, why did it do that? Because the plan exposes its intentions. It helps avoid hidden reasoning errors and step drift, where the agent forgot the original goal midway. It also makes it much easier to debug failures because you can compare what the agent planned to do with what actually happened during execution. If something went wrong, you can identify which step deviated from the plan. So when should you use this pattern? So you could use this pattern for multi-hop workflows where you need clarity on what's happening at each step. Or when steps might be done in parallel or benefit from an explicit order of execution. So basically, if you find yourself with a problem that's so complex enough that even you as a human would jot down a plan, it can be worth having your agent do the same. For us, in our travel planning scenario, this pattern would mean our agent first outlines a plan for a 4-day trip. For example, it might plan out, well, step 1, choose a destination that fits, let's say, October weather for hiking. Step 2, find flights for those dates. Step 3, find accommodation within budget. Step 4, schedule one fancy dinner reservation. And step 5, compile the itinerary and pricing into a summary for the user. So once the plan is set, the agent executes each step using our tools, via MCP, for instance, to search flights, check hotels, etc. And after executing all steps with the proper checks at each step, as we discussed earlier, the agent then summarizes the result, perhaps producing a nice 4-day itinerary. And that final summary is what it presents to the user. So by planning first and summarizing at the end, our agent's process is much more organized and transparent. If a detail was missed or something failed, it's easier to catch and correct during the process rather than only noticing it in the final answer. The last pattern is the supervisor loop. So this pattern adds a kind of oversight loop around the agent's operation. So imagine the agent is like a self-driving car, and the supervisor loop is the safety system that can grab the wheel or hits the brake if something goes wrong or when certain conditions are met. In practice, the supervisor loop means that after each step or after a cycle of steps, the agent doesn't just lightly move on. Instead, it evaluates the current state of the task. It asks questions like, have I finished the job? Did something go wrong? Am I stuck? Do we need a different approach? So based on that assessment, the agent's next action can change. It might decide to continue to the next step, or it might decide to handle an error, like try a different strategy or tool, or it even might realize it's done, or even like sometimes need to stop because it's hitting a limit or a budget. So what does this pattern help us prevent? So a well-designed supervisor loop prevents runaway loops where an agent might otherwise go in circles without end. It ensures that if something goes wrong, there is a fallback or a recovery strategy rather than just failing silently, or even worse, endlessly trying the same thing. And it makes termination conditions explicit, so you don't end up with inconsistent endings, like sometimes the agent stops after a single answer, or other times it accidentally keeps generating more steps forever. So in essence, the supervisor pattern adds a meta-level control flow that keeps the agent's overall process resilient and sane. when do we use this supervisor loop? Well, this pattern shines in situations where workflows are dynamic, and they may need branching or recovery. If your agent can potentially encounter unexpected conditions or might need to deviate from a simple linear path, a supervisor is your friend. It's also helpful to avoid non-terminating processes. You want a reliable way to decide when the agent should stop, if it's stuck, or when the task is complete. So how would this look in our trip planning agent scenario? Let's say our agent is in the middle of its planning and execution, and one of its tool calls, for example, searching for flights, times out. So rather than the agent just freezing or giving up, this supervisor logic can kick in and decide on a different path. Maybe try a backup API or present the partial results it has so far with an apology, or ask the user for guidance. Another example, if at some point the agent realizes a crucial piece of info, like budget or dates, is missing or invalid, then the supervisor can loop back, prompting the agent to ask the user for that missing piece, which ties back to our validation loop idea we mentioned earlier. So the supervisor might also keep an eye on how many steps have been taken and stop the process gracefully if it's clear no progress is being made, preventing infinite loops. So the supervisor loop is all about giving our agent the ability to self-correct and handle unexpected situations gracefully, much like a human supervisor would manage a project to keep it on track. Combined with the other patterns, it ensures also that our agent system can handle dynamic and real-world conditions without falling apart. All right, so we've covered a lot of pieces. Why agent fail in production, some of the solutions like RAG and MCP, and some of the design patterns to impose structure and reliability. Now it's time to put it all together. So let's walk through the reference architecture depicted here, using our travel agent scenario as context. So at the heart of the system is a central orchestrator. Think of this as the brain that manages the whole workflow. When a user's request comes in, the orchestrator, which could be implemented in LangChain, for instance, kicks off the process. It might first invoke our router agent to interpret the request. Then the router forwards the task to the right specialist agent, maybe the destination recommendation or itinerary planner. And the orchestrator then manages these agents' interactions, making sure each one does its part and passes the baton along properly until we get the final result. You can also notice a bunch of MCP servers representing our external tools and systems. Each of those tools, whether the recommendation or the destination agents, tools, servers, or maybe sometimes some internal services. They run as their own services, possibly each one hosted as an MCP server. Well, in this case, on a Docker container. So the orchestrator or the agents call these tools through the MCP interface, as we saw. What's cool here is that these tools can be written in different programming languages, and they can be maintained by different teams. But because they all speak the same MCP protocol, the orchestrator can talk to all of them in a consistent way. This is how we get scalability in development. You can have one team add a new tool in Python while another builds one in Java or JavaScript, and your central agent can use both seamlessly. We've also integrated observability and monitoring throughout the architecture. As the orchestrator and agent do their work, they're logging and tracing everything via observability stack. For example, using OpenTelemetry for tracing and metrics. This means we have full visibility into the execution logs, the logs to see the events, metrics for monitor performance, like how long each step takes, error rates, etc. And traces to see the end-to-end path of each request. So the observational layer here is very crucial for reliability because it allows us to monitor the system in production and quickly diagnose issues by seeing where things might be going wrong. Notice that the various agent design patterns we discussed earlier, the router, the specialist, the plan, execute, summarize, and the supervisor loop, they are not tied to a specific technology, but rather they are conceptual pieces you can implement within this architecture. For example, the router and specialist agents are part of the orchestrator's design. The plan, execute, summarize could be implemented inside a specialist agent, like the itinerary planner agent might internally do a plan, execute, summarize for organizing a trip. The supervisor loop might be an overarching logic in the orchestrator that keeps iterating through a plan until completion or failure. And the point is, this architecture is modular. You can slot in these patterns where they make sense without tightly coupling everything, which keeps the system flexible and maintainable. On the slide, there is a link for a blog post introducing the Azure AI Travel Agent, which is a flagship sample and reference architecture that uses MCP and those patterns in an Azure environment. It's a great reference if you want to see a real-life implementation of these ideas. But please keep in mind and remember that this is just a demo and it's not meant for production. So we're coming to the end of the talk, and I want to leave you with some practical guidance. Here's a checklist of key items to focus on when turning your prototype agent into a production system. Each of these points is something we've touched on during this session as a way of to mitigate the failures we discussed earlier. So idempotent tools and retries. So make sure the tools your agent calls can handle being called multiple times without causing unintended side effects. So if a tool action needs to be repeated, for example, due to a network glitch, which will happen, it shouldn't do harm if it runs twice or more. That allows you to implement retries with backoff on failures or timeout. So in our trip planner, if a flight booking attempt times out or fails, the agent can safely try again because the booking tool is designed to not double book the same flight if it receives the request twice. This dramatically improves reliability across multiple multi-step workflows by handling transient error gracefully. Schema validation and budgets. Use clear schema for data moving between your agent step and tools every time the agent produces an action or before it calls a tool. And also validate that the required information is present and correctly formatted. For example, before our agent moves from picking a destination to booking a flight, we check, do we have a confirmed date? Do we have destination city? Does it fit the budget? If not, the agent should pause and get that info. Remember the validation loop from earlier? So also, set budgets. By budgets, I mean limits on things like how many steps the agent can take, how many tokens it can use, how long it can run, and how many tool calls it can make, because budgets prevent the agent from running away or exhausting resources. For instance, they stop it from looping infinitely, or from using so much computation that it becomes too slow or expensive. Full workflow tracing, we talked about observability. Ensure you have traceability for the entire agent workflow. That means instrument your agent and tool calls so you can trace every step from the initial query to the final answer. If a user says what happened in that run, you should be able to pull up a trace and show, first, the agent did X, then Y, it called this tool, waited 3 seconds, got a response, then did Z, and so on and so on. This full trace, combined with logs and metrics, is essential for debugging. When something goes wrong, you will be thankful you can see the whole picture and not just the final error message. Production-ready system mindset. Finally, approach building these agents like you would do with any production system. I can't stress this enough. Treat the agent as a secure component that needs testing, monitoring, and clear interfaces. So use this checklist: item potency, validation, budget, tracing, etc., as a guide. The cool demo you start with needs hardening. So each of these items addresses a failure mode we discussed. For example, validation and budgets addresses the state drift and runaway issues. Timeout and retries address the timeout and partial failure issues. Traces addresses the observability and debugging challenges, and so on. So by systematically checking off these items, you ensure that your agent is not just smart, but also reliable. So to boil it all down, if you remember nothing else, remember these top 3 takeaways for reliability. 1, use schema validation between steps so the agent doesn't run with missing or malformed data. 2, implement timeouts and retries for tool calls, and design your tools to handle being called multiple times safely. And 3, trace everything so you can see what your agent is thinking and doing. These practices turn an AI agent from a fragile demo into a solid system. All right, so yeah, we've seen that making a good agent is about building a whole system around it. So as we wrap up, I want to say thank you for sticking with us through this talk. And I hope you found it insightful and that you're excited to apply these ideas. So thank you.
Thanks, Basim. It was absolutely insightful. We keep hearing, people about how easy it is to build a cool demo and how challenging it is to scale it and deploy it and move it from product to production. So we've got a couple of questions. I think we have time. We have some time to answer them now, and then maybe we can also continue the discussion on Discord in 10 minutes or so. So the first question was from Rich Parker about the routing design pattern. So he was asking, does the routing step just work, or do we need to develop rules? And if this is needed, which tool do we use to kind of define those rules?
Yeah, I mean, the simple answer is that, yeah, you need to instruct your agent to do the routing based on exactly some rules. Yeah, definitely. I mean, the LLM itself will not understand what it should be doing.
And then the next question from John Eric is, can you use semantic kernel and model routing in one app, or is it redundant?
I'm not sure about semantic kernel. I don't have experience with that. Do you have, Carlota?
Yeah. So yeah, my 2 cents is they are absolutely not mutually exclusive. Semantic kernel, which now has been integrated into Microsoft Agent Framework, is basically a framework for you to build agentic AI, while model routing is kind of an approach to have large language model designing, like identifying what is the best model to answer a specific query of your agent. And you can deploy it as a model instance in your Microsoft Foundry project. So you can definitely use both. You build your agent with a semantic kernel or Microsoft Agent Framework, and then as a model, instead of selecting one single model, you get a model routing instance. And then we've got some comments from another attendee about the willingness to deploy their AI agent, but they keep holding back until it's perfect. Any recommendation, Wasim?
That's hard actually. Because there is this whole security aspect. As I mentioned, your LLM, basically your app, will become a surface attack. So if it's not secure, please don't deploy it to publicly. But in terms of capabilities and response and everything, yeah, it really depends. I mean, it is publicly available to the public, or is it just internal to your company? If it's just internal, maybe you can just deploy it securely internally, so other folks can dogfood it and help improving it. But definitely not publicly if it's not ready.
Yeah, that's a good point. Like one of the kind of strategy you can take is starting with an internal use case. So you can have internal people in your company to test, as Wasim said, your agent. So you can also get some evaluation test cases that you can then use to assess your agent. So yes, as Wasim says, security is not an option. Make sure that you have observability, robust monitoring in place, and you have evaluation pipelines to evaluate both things like the groundiness, the fluency, the relevance of the agent responses, but also when it comes to agents, there's all the agent to calling accuracy. So if the agent is calling the right tools with the right parameters and all this kind of stuff. So there's lots of factors to take into considerations. Okay, a huge thanks for sending over these questions, and keep them coming, because again, in a few minutes, we're going to jump on Discord, and you can see on the screen the QR code to the event we are going to hold in a few minutes in Discord, and the link to join the event. It will be an informal roundtable. It's also very easy if you're not on Discord yet. It's very easy to join the event anyway, so we can continue our discussion. And also, as we shared before, and as we shared in the chat, a little reminder that Friday we're going to start the hack of this program, so the next phase, and you will be kind of the main character starting from Friday, because you are going to apply everything you have learned with this live streaming, AMA, discussions on Discord, and so on and so forth, to build your own agent and share it with the community. Any final thoughts, Wasim, before wrapping up and jumping to Discord?
Yeah, I mean, we live in an exciting time. So please have fun with these tools, try them, and make something useful.
Perfect. Yeah, looking forward to see what everyone will build within the app. And thank you so much again for joining us today, and see you on the other side. We'll wait for you on Discord.
Thank you all for joining, and thanks again to our speakers. This session is a part of a series. To register for future shows and watch past episodes on demand, you can follow the link on the screen or in the chat. We're always looking to improve our sessions and your experience. If you have any feedback for us, we would love to hear what you have to say. You can find that link on the screen or in the chat. And we'll see you at the next one.